Today, I will be presenting my lab report for Physics 2212. For this particular experiment, I measured the distance dependence of the magnetic field due to a small bar magnet and compared these measurements to the distance dependence predicted by equations for the on and off axis magnetic fields derived from the Boyd-Savart laws. To do this, I needed a bar magnet, the magnetometer app. I used a tape measure and painter's tape for marking. So because the bar magnet was not the only thing producing magnetic field, we had to take into account Earth's magnetic field. And to do this, I had to lay my phone flat on a table and keep turning it very slowly until I could get the x component as close to 0 as possible, taking into account Earth's north and south axis before doing the rest of the experiment. And I will talk about that importance later. So next I had to find the magnetometer chip in my phone. In order to do this, I laid my tape measure on the east-west axis and placed a magnet at one end. I turned my phone perpendicular to the tape measure and measured when the x value was its highest and the y value was its lowest at the same time. Then I placed a piece of tape on my phone corresponding to that. I did the same exact procedure, but turning my phone on axis and took into account when the x is at its lowest and the y is at its highest. Also placing a piece of tape there. And as you can see in the picture, I did a similar procedure where I found the chip in my phone. This spreadsheet was given to us to record each distance, so I then had to follow the instructions in the slides where I had to find a distance from the magnet that produced a magnetic field in the x component of the magnetic field with 20, and then do the same thing at 70, 120, 170, and 220. So I placed each distance in the distance column and placed each magnetic field in the magnetic field column, and in the spreadsheet computed the averages of each one, making a graph, as you can see to the right, which corresponds to my N and K value in the bar magnetic field formula given in the instructions. This is also the off-axis field. I only did it one time to compensate for time, of course, but this is what I ended up getting, accounting for the y value in Earth's magnetic field and my ultimate net magnetic field. While doing this experiment, I was able to conclude that of the statements given in the instructions, almost all of them were true. It just fully depends on if you're on axis or on perpendicular axis. Next, I had to construct a computational model, and doing the procedure, I was able to conclude that my dipole moment was 2.5-ish, as you can see. I then created a function for the magnetic field using the really rough formula given. Then we had to measure the magnetic field at different observation locations, 2 on axis and 2 on perpendicular axis. And as you can see to the right is where I laid out all of those. So those are 6 arrows that will be represented on the next slide. We then had to do one on another perp axis, but 45 degrees off the axis. So this is my graphical model showing all of the magnetic fields. As you can see to the right, the key tells you what each one is. And I, of course, scaled each one that would be accurate. So the closer they are, the bigger they are. And the on-axis ones are much larger than the perp axis ones. Some error within my experiment were probably mostly here in my coding. As you can see, my 45-degree magnetic field did not come out as a full number. That one was a little bit harder to orchestrate around, but in the end, I still get the idea and was still able to plot it. So what if I hadn't accounted for the Earth's magnetic north? So if I hadn't compensated for the magnetic north, my experiment results will have included vector contributions from Earth's magnetic field at an angle, which leads to inaccuracies in both the magnitude and direction of my magnetic field measurements. So by aligning it up with the magnetic north, I was able to isolate the magnetic field, reduce angular and vector error, and also improve my accuracy. So what if I redid the experiment, but instead of using one magnet, I used 2? If I used 2 identical magnets, then the field strength of both would increase. The field range would also extend further from the magnet. Field distribution would still be dipole-like, but with a much higher dipole moment. Obviously, measures would be larger values, and my error would probably be reduced because of the longer distances and stronger signals. Thank you.